Hi, my name is Gundete Manoj from Department of Chemistry, roll number 21CY 23005.
Hello everyone, my name is Vikyat Gomadi. I am from CSC department. My roll number is 21CS30070. Hello everyone, today I'll be presenting a method called multitask self-supervised time series representation learning. This method aims to improve how we extract meaningful information from time series data. As we know, time series data will be changing over time. For example, like stock prices and weather records or sensor readings, these data change over time. Let's see how we will work on this data. To start with, let's talk about why time series data is important. Time series data is everywhere from IoT sensors tracking temperature to financial systems recording stock prices. Analyzing the data helps in making predictions and identifying patterns. But here comes a big challenge. Labeling this data is hard. For example, imagine trying to label every heartbeat in a ECG or making every point of an unusual activity in network traffic, which is impossible, or you can say it is more time consuming and costly. And the main problem we face is that traditional deep learning models need a lot of label data to perform well. But since labeling time series data is difficult, we need better methods that can work effectively with minimal label data. This is where self supervised learning comes in. It is a technique that uses the data itself to guide learning without needing labels. Self supervised learning offers a great solution for this by learning useful features from unlabeled data. But here's a catch: existing self supervised models still face some limitations, and that's where our research comes to solve those problems. So, what exactly is self supervised learning? Imagine you are trying to solve a puzzle without having the picture on the box. Instead, you figure out how the pieces fit together by recognizing the patterns. Self supervised learning works in a similar way. The model trains itself by solving small challenges within the data. In images, a common task might be predicting the color of a grayscale image or solving a zigzag puzzle. By completing these tasks, the model gradually learns useful features. Now, for the time series data like stock prices or heart rate signals or weather signals, we can train a model by asking it to predict the missing data or detect pattern in trends or compile values from different parts of sequence. These tasks help the model understand the structure of data without requiring labels. Self-supervised learning has already shown strong results in computer vision and NLP, but time series data has unique challenges. For example, data points are heavily dependent on earlier values, and here trends change quickly. Developing self-supervised methods, especially for time series data, is still a growing field. To better understand the challenges of learning from time series data, let's look at the two main approaches. Those are pretext text, pretext task, and contrastive learning. Let's go through one by one. First, let us go through pretext task. This involves creating an artificial task for the model, like predicting masked data points. While this method works, the feature it learns may struggle to generalize to new tasks. This happens because the model may focus too much on the specific pattern it learned during the artificial task. For example, if the model was trained to predict the missing data points in short sequences, it might fail to perform well when asked to analyze longer trends or identify anomalies. Essentially, the model becomes too specialized for one task and lack the flexibility needed to adapt to different problems. Now let's come to contrastive learning. Here, we train the model to recognize the pairs of data points that are similar and distinguish those that are different. Imagine two sections of time series that follow similar patterns. These are treated as positive pairs. Meanwhile, the points that are unrelated are treated as negative pairs. By learning to group similar data together, contrast to learning helps the model identify important features. However, this method still faces some limitation. Those are, for example, time series transformer struggles to adapt when the target task is very different from the one it was trained on. And using the T-loss, here we face issues because using the T-loss method only focuses on comparing smaller subseries, which limits its ability to capture broader trends in the data. Using temporal neighborhood coding, here this model relies on sampling nearby points in the data, which can fail if the data patterns are inconsistent or noisy. Whereas in case of time series temporal and contextual contrast to learning, here the model performs poorly when the data contains noise or when understanding long-term trends is essential. These limitations highlights the need for a method that combines multiple strategies to get accurate results, and that's where our proposed method comes in. Hmm. Our proposed methods combine three key ideas. Those are contextual consistency, temporal consistency, and transformation consistency. Let's go through them one by one. Contextual consistency. Here, we are ensuring that data points that appear in similar context are treated as similar. This helps the model understand data points within different contexts, ensuring that the points in similar environments have similar representations. Next, let's see temporal consistency. Here, we ensure points that are close together in time have smooth patterns. This model focuses on identifying patterns that belong to same smooth sequence, reducing noise in the model understanding. Whereas transformation consistency, here we make sure the model understands the data even when it's modified slightly, so that we can ensure that the small data modification like scaling or jittering don't confuse the model. Using the combining these three key ideas, we are proposing a new method where we can train on time series data. Additionally, we introduce a uncertainty weighing approach that helps balance the contribution of these tasks during training. By combining all three, our model learns richer, more flexible representation that improves its ability to handle real-world time series data. Now let's come to the architecture details. The core of our method is a shared encoder, which is a neural network designed to extract useful features from time series data. This encoder has three parts: an input projection layer that turns raw data into a more useful format for learning, a timestamp mask module that randomly hides parts of data to create a prediction challenge for the model. This helps it learn patterns more effectively, and a dilated CNN model that captures information across both short-term and long-term patterns. As you can see from this diagram, we will be passing the data through three layers. Those are input projection layer, timestamp masking layer, and dilated convolution layer. After that, we will be applying the three consistencies, and we'll be combining them through the uncertainty weight approach to get the final loss. So this is the overall architecture of the multitask self-supervised time series representation learning. Now I'd like to invite my friend Manoj to continue with the presentation.
Good afternoon, everyone. My name is Gundeti Manoj. Let's dive into the core of their method, starting with contextual consistency. Contextual consistency is a crucial component of their framework. The main idea here is to encourage representations of overlapping timestamps in different contexts to be consistent. They implement this using a contrastive learning approach proposed by TS2WEC. Here is how it works. They start with an input time series and generate two overlapping segments using random cropping. These segments are fed into their shared encoder, which maps them to timestamp level representations. Then they perform two types of contrasting: timestamp wise and instance wise. In timestamp wise contrasting, They treat representations at the same timestamp from two augmented views as positive pairs. This helps the model learn discriminative representations over time. For instance-wise contrasting, they aim to learn discriminative representations at the same timestamps across different instances. This is crucial for distinguishing between different time series. The power of this approach lies in its ability to capture contextual information at multiple resolutions, which is essential for understanding complex time series data. Moving on to temporal consistency, they use the idea that neighboring time segments often have similar properties. This is particularly important in time series data where local smoothness plays a significant role. They implement temporal consistency using the approach proposed by temporal neighborhood coding. They consider the two overlapping segments from contextual consistency as a neighborhood pair. Then they obtain non-neighboring segments using statistical testing. The model learns to distinguish between neighboring and non-neighboring pairs. This approach is based on the assumption that time segments in neighborhoods have similar properties while those in non-neighborhoods are different. By learning this distinction, their model can capture the temporal dynamics of the data more effectively. They use a discriminator to estimate the probability of a neighboring pair, and their loss function is designed to mitigate sampling bias using positive unlabeled learning. The third key component of their framework is transformation consistency. This is crucial for learning representations that are invariant to certain transformations of the input data. They implement this using an approach inspired by time series transformation consistency contrastive learning. Here is how it works. They apply weak and strong augmentations to the overlapping region of their input segments. These augmented views are considered positive pairs. They use a contrastive learning approach to maximize agreement between these augmented views. The weak augmentation adds random variations and amplifies magnitude, while the strong augmentation involves shuffling subseries and adding jitter. This helps their model learn representations that are robust to various transformations that might occur in real-world time series data. Now let's discuss how they combine these three consistency approaches into a unified multitask learning framework. This is where the real power of their method lies. They use an uncertainty weighing approach proposed by Kendall. This allows them to dynamically adjust the contribution of each task during training and handle different tasks with varying scales and units and also optimize multiple objectives simultaneously. Their final loss function is a weighted sum of the losses from each consistency task with learnable parameters determining the weight of each task. This approach enables their model to learn general representations that capture various aspects of time series data. To evaluate their model, they conducted extensive experiments across three downstream tasks: time series classification, forecasting, and anomaly detection. For classification, they used the UEA archive, which contains 30 multivariate time series dataset. They also used the human activity recognition dataset and a fault diagnosis dataset. For forecasting, they use the electricity transformer temperature datasets, which include power load features and oil temperature targets. For anomaly detection, They use the Yahoo and KPI datasets, which contain various types of time series anomalies. These diverse datasets allows them to thoroughly test the generalizability of their learned representations. Their results on time series classifications were particularly impressive. On the UEA archive, they achieved the highest average accuracy of 0.725, outperforming all benchmark models. Their method achieved the best accuracy on 14 out of 29 datasets. They significantly outperformed other methods on datasets like archial fibrillation and Standwalk jump. These results demonstrate the effectiveness of their multitask approach in learning discriminative features for classification tasks. In time series forecasting, their method showed robust performance across different prediction horizons. On the ETT datasets, they achieved the lowest average mean absolute error on all three datasets. Their method was particularly effective for long-term predictions, outperforming even specialized forecasting models. This showcases the ability of their learned representations to capture long-term dependencies in time series data. For anomaly detection, their method achieved state-of-the-art performance. On the Yahoo dataset, they achieved the highest F1 score of 0.754. On the KPI dataset, they again achieved the highest F1 score of 0.678. These results demonstrate that their learned representations are effective not just for predictive tasks but also for detecting unusual patterns in the time series data. To better understand their learned representations, they conducted a qualitative evaluation using TSNE visualization. Here are some key observations. Their method clearly separates different classes in the learned representation space. Their method outperforms other representation learning approaches in terms of class separability. The separability improves significantly compared to the original data space. They quantified this using Silhouette score, which measures how similar an object is to its own cluster compared to the other clusters. Their method consistently achieved higher Silhouette scores, indicating better quality representations. One of the most exciting aspects of their work is the transferability of their learned representations. They conducted experiments on a fault data diagnosis dataset with four domains. They pre-trained their model on one domain and fine-tuned it on other. Their method showed excellent cross-domain performance, often achieving near perfect accuracy. This demonstrates that their method learns truly general representations that can be applied across different domains. In conclusion, their multitask self-supervised learning. Okay. In conclusion, their multitask self-supervised time series representation learning framework offers several key advantages. It combines contextual, temporal, and transformation consistency to learn comprehensive representations. It outperforms state-of-the-art methods across various downstream tasks. It learns transferable representations that can be applied to different domains. It provides a unified framework for learning from unlabeled time series data. Their work opens up new possibilities for leveraging large amounts of unlabeled time series data across various domains. And looking ahead, There are several exciting directions from future work, exploring additional self-supervising tasks that could capture other aspects of time series data and applying their framework to even more diverse domains such as healthcare or finance is the interesting one. Thank you.